Simplex method is considered as invisible when all the variables in entering column are negative. B. Variables in the basis are negative. C. Artificial variables are present in basis. D. Pivotal value is negative. As we know, simplex method is a standard technique of solving linear programming problem or an optimized solution, typically involving a function and several constraints expressed as inequalities. The inequalities define a polygonal region, and the solution is typically at one of the verticals. Some special cases of simplex methods are unbounded solution, invisible solution, multiple solution, and degenerated solution. So, simplex methods respectively is considered as invisible when artificial variables are present in basis. In this case, we compute simplex method as invisible. This is the reason of invisibility of simplex method is the presence of artificial methods or artificial variables in its basis. In the simplex method, if in the pivot column all the entries are negative or zero, when choosing leaving variables, then in this case, if the pivot column of all the entries are negative or zero, when choosing leaving variables, then solution is degenerate, solution is invisible, alternative optima or bounded or unbounded solution not attempted. Simplex method, it is a step-by-step in which a solution is started with initial visible solution, and in the next step the initial visible solution improved. The steps are repeated until the optimal solution is reached. Accordingly, In this case, we assume that either solution is degenerate or invisible or alternative optima or unbounded or not attempted. Let us see more explanation in the next slide to understand what do we mean by negative entries in the pivot column and the effects of these negative entries on the nature of solution for simplex method. Following are the set of variables in simplex method. There are main 5 variables used in simplex method. Artificial variable. This variable is introduced in case of greater than or equal to type constraints to not violate the non-negativity constraint. Basic variables. They can be defined as the variables which can take any value other than 0. This is known as basic variable. These variables which can take any value other than 0. Non-basic variables. This variable is not in the basic solution. Non-basic variable is not in the basic solution and is having the value 0. Its values equal 0. Slack variable. This variable is introduced in the simplex method to eliminate less. So surplus variables. These variables is introduced in simplex method to eliminate greater than. So gives a question about the listing of the main variable or main variables in simplex methods. So the answer is artificial variable, basic variable, non-basic variable, slack variable, and surplus variable. In various instances, we use these variables. In various instances, we use these variables either for the big M at the form of simplex method or two phases methods, or to convert the inequalities into standard form, from canonical to the standard form, by adding or subtraction the Celiac variable s usually. So this is the main variables of used actually in the simplex methods. We saw artificial variables very clearly is used in big M methods and two phases methods. Non-basic and basic variable are usually present in each form of simplex. Slack variable mainly we use it in the simplex method as well as in the big M. Its function to convert to the standard form the inequalities. Surplus variable also is known to balance the inequalities. Okay, please we will try to test you to understand the method of graph. One unit of product B requires 3 kg of resources R1 and 1 kg of resource R2, while 1 unit of product B2 requires 2 kg of R1 and 2 kg of R2. The profit per unit by selling B1 and B2 is 2000 and 3000 respectively. The manufacturer has 90 kg of R1 and 100 kg of R2. The manufacturer can make profit of, so these are the options given. One, $60,000, two, $135,000, three, $150,000, and four, $200,000. The correct answer is $135,000. To find or to prove this answer, you have to use the graphical methods. As you would now just see, we have two products, X1, X2, of course, and two resources, R1 and R2. That's why two constraints, one for R1 and one for R2. Of course, the problem is about maximization profit, so the constraint should be less or equal than the total available resources. So as you see, we will not see intersection point as it is two constraints represented by two curves, but not intersected, and accordingly the corner points is appeared. So accordingly the perfect answer in this case is not the B point or the C point. For example, C point is assumed as the intersection point between the two curves. 135,000 is an optimal solution. Okay, example 3. Solve the following LPP linear programming problem by using simplex methods. Given the objective function max z equals 6x1 plus 4x2. So this problem deals with two decision variables and x1 and x2, and the parameter for x1 is 6, which indicates the profit of 1 unit of x1, and for the parameter of x2 denotes the profit of 1 unit of x2. Subject to the constraints x1 plus 2x2 less than 720, 2x1 plus x2 less than or equal 780, and the last constraint is x1 less than 320, the non-negativity condition x1 x2 more or equal 0. So let's move. As we experienced before, let's follow the mentioned below the steps. Step 1. Convert the constraints into the standard form. Standard form means add or subtract slack variable s. So the constraints will take the following shapes: x1 plus 2x2 plus s1 equals 720, 2x1 plus x2 plus s2 equals 780, and the last constraint is x1 plus s3 equal 320. This is the first step, as we emphasized before, to convert the constraints or inequalities into the standard form. Step 2, to convert objective function into zero equation. So we are going to move the two decision variable to the left side, and we will get z negative 6x1 negative 4x2 equal 0. So the next step is to design the primal table. Or essential table, or table number 1. First step, convert the constraints or inequalities to the standard form by adding s or slack variable. The second step is to convert objective function into zero function by moving the right side to the left side, and then we will get zero function. Okay, this is what you call it primal table or essential table or table number 1, referring to the standard form of constraints. So this table will be designed. So the first upper row consists of the basic variable or non-basic variable, which now is are x1, x2, s1, s2, s3, and solution. The status of mentioned variables now is non-basic variable. Our target is to remove x1, this non-basic variable, from the condition of non-basic to the condition of basic variable. Instead of s1, s2, and s3. Now, before the process of solution or the iteration, the left column consists of 3 variables, which are known now as basic variable. No? So our objective is to remove non-basic variables to the basic variable, replaced s1, s2, and s3. To implement this target, step 1 or step 4 now, to determine the entering variable. Entering variable defined as that variable which faces the biggest negative value in the row of the objective function, or z row. So the biggest negative value as shown is here. We have two negative values. x1 faces -6, x2 faces -4. So x1 should be considered as entering variable because it faces -6, which is the biggest negative value in the last row of Z. So step 5 is to find or to determine exiting variable. Now, as we mentioned before, by division, the column of solution by the column of x1 except negative and zero values, the exiting variable is S3. Now let's check. $720 over 1 equals 720. $780 over 2 780 over 2 is more, of course, than 320. Is more than 320. Actually, 780 over 2 is 390. So the result of this division is 720, 390, and the last division is 320 over 1 equals to 320. Now S3 is considered as exiting variable. The pivot element is the intersection point between the row of exiting variable and the column of entering variable, which is 1. The pivot equation S3 existing variable or pivot element 1 triple 0 1 320 over 1. Okay, so the value of x1 in the next table instead of S2 is 1 triple 0 1 320. So now this is the main equation. We will use it later to calculate the change in other basic variables like S2, S3, and also Z. Now we will depend on pivot equation to continue our solution. Now focus on this pivot element. Also, it is the values of x1 in the next table. Let's continue. Reformulation of new table based on the entering or entrance of x1 as new basic variable. The entrance of the x as new basic variable will lead to the change in S1, S2, and Z. In this case, we will follow the following rules. First, we have to determine the pivot elements of S1, S2 and Z. The pivot element of S1 and S2 and Z is the intersection point between the rows of S1, S2 and Z and the entering variable, which is x1. Okay, these pivot elements of this variable should be multiplied by the pivot equation and subtracted from the original values of S1, S2, S3. Okay. Looking at the primal table, the values of S1 are 1, 2, 1, 00, 720. The result of multiplication of the pivot element of S1 by the pivot equation equal 1, 0, 0, 0, 1, 320. By subtraction, these values from the original values of S1, we will get new S1. 1, 2, 1, 0, negative 1, 400. This is the values of S1 in the next table. The same sequences will be used for S2 and for Z. Just repeat the same procedure. The process of reformulation of the non-basic variables S1, S2 and Z, we will get table 2, secondary table. This of course is a process of iteration of solution. So the new table consists of three basic variable. Now x1 is the new basic variable instead of S3. Now let's repeat the same steps in order to find or to determine the new entering variable and the new exiting variable. Using the same tools, now x2 is entering variable and S1 will get out is exiting variable. The element is 2, intersection point between the column of x2 and the row of S1. The pivot equation is the result of division of S1 over S1 over 2. S1 over 2, we will get a pivot element and also the values of x2 in the table number 3. As we mentioned before, x2 is entering variable while s2 is exiting variable, and pivot element equal 2. Accordingly, pivot equation equal s2 over 1. What do you mean by the variable s2 over 1? So x s1 s2 over 1 equal 1 0 1 0 1 negative 2 and 140. So now this is a pivot equation as well as the value of x2 in the next table. Reformulation of variable based on the appearance of x2 as basic variable. The change will occur s2, x1 and z. The impact of entrance of x2 as basic variable on s2, x1 and z. Let us see in the next slide which changes will occur. Okay, by repeating the mentioned procedure of measuring the entrance of new variables as basic variable, we will get the new s1 equal 0 0 0 negative 2 3 120. The new x1 as it is 1 triple 0 1 320, and new z is 0 0 0 4 negative 2 2480. Let's move to the third table and to see if the iteration of solution is stopped. Okay, this is table 3. It seems the last table of iteration. Now just focus on the values of z. 0 0 0 4 negative 2. The rule states that the iteration of solution and the optimal solution will be captured when the negative values in z row will disappear or disappeared. Now as you see, the function z has no negative values. Mainly we mean by the negative values that values which faces the basic variable x1 x2 actually, not which faces s1 s2 and s3. As we mentioned before, s1 s2 s3 as slack variable, because we designed these variables to process the solution of simplex method. They are not an original variable. We created this variable. So look to the table as a whole and see the value of S1 equal 120. Focus on the last or look at the last column of solution. X2 equal 140, X1 equal 320, and Z equal 2480. So, but this is not the last station. Now we have to look after the proof of these findings, the application of these findings to what? To the objective function and to the constraints in order to correct them. Application. Example 1. The assignment cost is assigning any one operator to any one machine is given in the following table. Machine operator. Now, the matrix consists of 4 machines against 4 operators. Each machine should be assigned to one operator. The condition is satisfied. 4 machines and 4 operators. The cells inside this matrix contains the cost of assignment. For example, if we assign A to 1, then it costs 10. If we assign B to 2, then it costs 9. If we assign C to 3, then it costs 3. If we assign D to 4, then it costs 7. The requirement is to find the optimal solution using Hungarian methods. Remark, the red numbers represent the matrix, the body of the matrix. Now, this problem gives 3 machines and 3 operators. Each operator assigned to one machine, and each machine should be assigned to one operator, as we mentioned before, on the basis of 1 to 1, on the basis of 1 to 1. Now we are going to apply the Hungarian methods using the previous steps or instructions. Subtraction or row subtraction, then column subtraction, then to draw the lines which will cover the rows of column which contains a minimum number of zeros. If the lines equals the number of columns or the number of rows, then we get an optimal solution. To reach the optimal solution means that the lines should equal the number of lines should equal the number of rows or column. The expected number of lines is 4. The number of lines is 4. 4 equal number of columns, 4 equal number of rows, 4. Okay. The practices of row subtraction. خفض الصفوف وتنقيص الصفوف وطرح الصفوف. Now, referring to the given matrix, the cost inserted in the first row are 10, 5, 13 and 15. The least cost in this row is 5. Please refer to the given problem. Now we are going to subtract the smallest cost, which equals to 5, from each element of this row. Then 10 minus 5, 5 minus 5, 13 minus 5 and 15 minus 5. The result is 5, 0, 8, 10. Then move to the row number 2. Check your given problem. In the row number 2, the costs inserted in this row are 3, 9, 18, 3. Then the least cost is 3. Should be subtracted from the remaining elements of this row. 3, negative 3, 0. 9, negative 3, 6. 18, negative 3, 15. And 3, negative 3, 0. Move to the next row. Row 3. The cost inserted in this row are 10, 7, 3, 2. The least cost is 2. These 2 should be subtracted from the remaining cost. 10 minus 2, 7 subtracted by 2, 3, negative 2, and 2 minus 2. The result is 8, 5, 1 0. The last row is consisting of cost 5 11 9 7. The least cost in this row is 5. Then 5 should be subtracted from the remaining cost. Then 0 6 4 2. As you see, each row, the first row got 1 0, the second row got 2 zeros, the third row got 1 0, and the last row got 1 0. At least, when we mentioned before that, at least row should get 1 0, except column number 3 has no 0. Of course, the number, now we are not going to apply the lines. We are going to jump to implement the second operation, which is known as column subtraction, using this matrix. We will apply the operation of column subtraction using the matrix after the row subtraction, not referring to the origin problem, referring to the problem after the row subtraction. Okay, put into account. We will deal only with new matrix, after the operation of the row subtraction. Okay, we are going to choose the least cost from this given matrix. Now, referring to the previous problem, just look to the previous problem and focus on the columns. Now, the least costs, we are going to choose the least cost in each column. For example, referring to the previous matrix, the least cost is in the previous is 0. So if we subtract 0 from the remaining cost, the column is remain as it is. Also, this case is applied to the next column and to the last column, except the column 3. The least cost in the column 3 is 1. This one should be subtracted from the previous, from the other cost. Then we will get 7, 14, 0 and 3. Now each column and row has minimum number of has minimum number of zeros. Now the next step, we are going to cover using lines to cover the rows or the columns which consists of zeros. So we can of course easier column 1, column 2, column 3 or column 4, or row 2, row 3 and column 1 and column 2, whatever. Now the number of lines equals the number of columns equals the number of rows equal 4. Then the assignment is said to be optimal. Respectively, machine A should be assigned to operator 2, cost equal 5. Machine B to problem or to operator 4, cost equal 3. C to 3, cost equal 3, and D to 1, cost equal 5. The total cost is the summation of the costs 5 plus 3 plus 3 plus 5 equals 16. So when we assign machine A to operator 2 and B to 3 and C, B to 4 and C to 3 and D to 1, we will get the minimum of the cost of assignment for machine to 4 operators. This is what is known as the Hungarian model in its, of course, simple way. Example 2. Player A has 3 strategies, or player B has 5 strategies. As we mentioned, it is not meaningful to start a comparison with columns or rows. Just satisfy the rules of dominance. This is a main requirement. Now let's look to the columns. C1, the values of C1 compared to the values of C2. Look at C1, you will see that 1 is less than 3, but 3 is more than 4, and 6 is more than 4 also. So the comparison between C1 and C2 doesn't satisfy the rule of dominance. Now let's move to compare C1 and C3. 1 is less than 2, 3 is more than 1, and 6 is less than 7. We will also ignore this comparison. Now move to the comparison between C1 and C4. C1 is less than C4 because 1 less than 7, 3 less than 5, and 6 equal 6. So C4 respectively is dominated by C1, or C1 is dominating C4. Therefore, C4 will be eliminated. Now, following the same process, let's compare C2 with C5. We remark that looking at C2, 3 is less than C4, 4 is less than 6, also 4 is less than 5. So C5 is dominated by C2 because the values of C2 is less than the values of C5. Therefore, C5 will be eliminated. There remains in 3 columns and 3 rows. Look to the arrow, the blue one. Now we got new matrix after the operation with columns. The matrix, which consists of 3 columns and 3 rows. Now let's try to apply the rules for rows. Compare ray 1, ray 2 and ray 3. Check please if the values of R3 are more than the values of R2 or equal. 6 is more than 3, 4 is equal 4, and 7 is more than 1. Since A plays for maximum, R3 dominates both R1 and R2 because the values of R3 is more than the values of R1 and R2. Therefore, R1 and R2 will be deleted. The third matrix consists of 1 row and 3 columns. C1, C2, C3 and R3. Because player B has three strategies, C1 and C2 and C3, while player A had one strategy, and player B all time plays for minimum, not maximum. That's why we choose 4, because it's the minimum value. It is a minimum value because player B plays for minimum, while player A plays for maximum. We ignore player A because he has only one strategy, R3, and player B had 3 strategies, C1, C2 and C3. That's why we choose 4 as game value. Optimal strategies for A, he has no strategies, he has no first or second strategies, but he had the third strategies, so 0, 0, 1. For player B has 5 strategies, but he choose strategy number 2. That's why his optimal strategy is 0, 1, 0, 0, 0. Okay. Example 2. Given primal as linear programming problem of minimization. We need to convert this primal problem to the dual one. Okay. The components of the primal are usually objective function, main W is about minimization. Objective function consists of 3 variables, y1, y2 and y3. The decision variable of these objective functions are 3, y1, y2, y3. The coefficients of these decisions or decision variables are 2 the cost of 1 unit of y1, 10 is the cost of 1 unit of y2, and 12 is the cost of 1 unit of y3. Also, given two constraints, y1 5 plus 5 y2 plus 3 y3 greater or more than 5. The second constraint y1 plus 2y2 plus 8y3 more or equal 3. Now once we have 3 decision variables, then the non-negativity condition represents these 3 decision variables or variables y1 comma y2 comma y3 comma should be more or equal 0. Our duty is to remove this primal problem to the dual one. Again, let's remember the instructions or the step of conversion. First, minimization becomes maximization. W becomes Z. Y becomes X. Right. The variable of the dual should equal the constraints of the primal. The primal gives 2 constraints, then the dual will consist 2 variables. It will be x1 and x2. The parameters or coefficients of the objective function will be the constants of the constraints of the primal. 5 will be the coefficient of x1, 3 will be the coefficient of x2. Then the objective function of the dual will take the following equation: max z equals to 5x1 plus 3x2. Let's step forward. How to design the constraints of the dual. The numbers of the constraint in the dual or of the dual equals to the number of variables in the primal. The primal has 3 variables: y1, y2, y3. Then respectively the dual will contain 3 constraints. The first column of the constraints of the dual is the first row of the primal, and the second column of the dual represents the second row of the constraints of the primal, or the first the first constraint in the dual is the first column in the primal. The second constraint represents the second column in the primal. The last row of constraint in the dual represent the last column of constraints in the primal. Now, as we mentioned, the constraints of maximization all time is less or equal. Constraint number 1, x1 plus x2 less or equal what? Equal the coefficient of y1, which is 2. The second constraint, 5x1 plus 2x2 less than or equal 10. What is 10? 10 stands behind what? The coefficient of the second variable. 10 is the coefficient of y2. 12, 3x1 plus 8x2 less or equal 12. What 12? 12 is the parameter of what? Of the variable y3. Then 3 constraints equals 3 variables in primal. Two variables in the dual equal 2 constraints in the primal. Okay. Now, the variables in the dual are y1, y2, y3 more or equal 0. The variables in the dual are 2 only, x1, x2 more or equal 0. Please, actually the primal problem in example 2 was the dual in example 1. Please step back to the example 1. You will find that we remove the dual option in example 1 to the primal problem in the example 2. We can play with this game as long as we need. Now, so how to the conversion of minimization to maximization and the conversion of maximization to minimization. This is very easy and very excited practices. We will go deep to explain and identify the features of this problem. Okay. Refer to previous steps. Let us introduce how to construct a table of payoff. A manufactures 3 types of products: product A, product B, and product C. Each of these products has its fixed cost and variable cost. For example, product A has a fixed cost of $25,000 while its variable cost of $12. Product B has $35,000 while its variable cost is $9,000, of course. Product C had $53,000 while its variable cost equal $7,000. Now, each product faces three levels of demand: poor demand, moderate demand, and high demand. So, for example, if product B faces moderate demand, then the demand of product B equal 7,000 units. If it faces poor demand, then the demand of product B equal 3,000 units. Now, we have three products. Each of them faces three levels of demand: poor, moderate, and high. Then the conditions or the phases or the forms of total demand are 9. 3 products multiplied by 3 phases of demand or 3 levels of demand. Product A has 3 levels: poor, moderate, and high, respectively product B and product C. So there are 9 levels of demand. Now, given the price of unit equal $25, then we can easily conduct a table of based on this, on the given data, the payoff table. Now we would like to learn how to build a payoff table according to the given information and data. Okay. Required: if the sale price of each type of product is $25, then prepare the payoff matrix. Assume D1, D2, D3 denote poor, moderate, and high demand, respectively. Payoff equal sales revenue, the price multiplied by quantity. The revenue equal price of one unit multiplied by the quantity of the product, negative total cost. Total cost means fixed plus variable cost. Fixed is given, variable cost, it is the quantity of product multiplied by the variable cost. So the calculations for payoff for each pair of alternative demand, which is course of action, and the types of product state of nature are shown. طيب. D1A, it is, what do we mean by D1A? Demand of product, poor demand of product A. D1P means poor demand of product P. D1C means poor demand of product C. Okay, now the common quantity of these three products as poor demand is 3000. So the revenue of all types of product A, product B, and product C should equal 3 multiplied by 25, because 3 is the quantity demanded as poor demand is 3000 units, and the price is fixed equal $25. So the operation 3 times 25 is common between these three types. Negative 25 also, no, negative 25 is depends, it show the fixed cost of product A, 35 the fixed cost of product B, and 53 the fixed cost of product C. Also the variable cost is different, 12 for A, 9 for B, and 7 for C. So the poor demand of product A is 3 times 25. 3 is quantity, 25 is price, negative 25, it is fixed cost, negative 3, it is a quantity, times 12, 3 times 12 is a variable cost. The result is 15. D1P, poor demand for product B, is 3 times 25. 3 is poor demand of B, 25 is the price, negative 3, 35 is the fixed cost of product B, and negative 3 is the quantity of poor demand, times 9. 9 is the variable cost of product B, 13. The poor demand of C also equals 3000 units. Multiply by the price is 25. Negative 53. 53 is the fixed cost of product C. Negative 3 is the quantity, the poor quantity of demand, and times 7. 7 is a variable cost of product C. Okay, let's move to the moderate demand. The moderate demand for each product equals 7000. Then for A is 7,000 multiplied by 25, the price is constant, negative 25, the fixed cost of product A, times 7, negative 7 times 12, which is 66. Moderate demand of product B is 7,000 unit times 25 is price, negative 35 is the fixed cost of product B, negative 7 times 9. 9 is the variable cost of product B. The moderate demand for product C is 7. 7 is common quantity between these three types of product, times 25 sell price, negative 53 is the fixed cost of product C, times 7, negative 7 times 7 is the variable cost of 7,000 units. The result is 73. Now, etc. The shown table stands for the various demand A, demand B, demand C, and depends on the various level of demand. For example, A when demand is poor is 14, when demand is moderate is 66, when demand is high is 118. So this is the events, and this state of nature, and this A event is the course of action, and alternative demand is the state of nature. For product B, when demand is poor is 13 units, when demand is moderate 77, when demand is high is 141 respectively. For product C, when demand is poor, the quantity demanded is 1 unit. When demand is moderate, 73 is demanded. When demand is high, so 145 units is demanded. Now, this how to construct a payoff matrix using various givens. Referring to the previous slides, let us add the last step 5, finding the optimal solution. The value of Z at various points of the region of visible solution are calculated. The optimum, maximum or minimum Z among these values is noted. Corresponding solution is the optimal solution. Let's see. Solve the following LPP, linear programming problem. LPP stands for linear programming problem graphically. What is given here? At maximum or max Z equal 3x1 plus 5x2. That's mean. Firstly, this linear programming problem about what? About profit maximization. Once it indicates max z. There are two decision variables, x1 and x2. 3 is the profit of 1 unit of x1, while 5 is the profit of 1 unit of x2. Now, subject to the following constraints: x1 plus 2x2 less or equal 2000, x1 plus x2 less or equal 1500, x2 less or equal 600. These three constraints means that these two products, x1 and x2, pass 3 phases of production or 3 machines or whatever, 3 processes respectively. And actually x1 is a non-negativity condition, x1 and x2 more or equal 0, obviously. So let's step by step view how we can apply graphical method solution. First, to represent the constraint graphically in inequalities are written as equalities. Every equation is represented by a straight line. 2. To draw the lines, 2 points on each of the lines are found as indicated in the following table. Intercept. Now, step 1. Convert the constraints into what? Into equations. First step, to convert the constraint into equation. What that means? That means constraint 1 will equal x1 plus 2x2 equal 2000, and x1 plus x2 equal 1100, and x2 equal 600. 3 constraints. So using geometrical methods to find the value of x1 when x2 equals 0, and to find x2 when x1 equal 0. Let's see how we can do this. Okay, check this table. This table contains 4 columns and 3 rows. Equation: x2 intercept when x equals 0, x1 intercept when x2 equals 0, and this is a point x1 x1 and x2 on the line. Okay, now Check the first equation. x1 plus 2x2 equal 2000. If x1 equals 0, then the remain is 2x2 equal 2000. x2 equal 2000 over 2, 1000. If x2 equal 0, then x1 equal 2000. So the points 0, 1000 and 2000, 0. So the common is 2000, 1000. Now let's go to the next equation. x1 plus x2 equal 1500. Of course, x1 equal 0, x2 equal 1500, x2 equal 0, x1 equal 1500. Okay. x2 obviously equal 600 and x1 equal 0. x1 axis, x2 equals 0, x2 axis. So plot each equation on the graph. Now we are facing three equations where the first point, three equations corresponding three constraints. Now we are going to plot these three equations on the graph. Let's see how we can do this. Firstly, x2 equals 600 when x1 equal 0. This is the last. So the common points for the first constraint 2000, 1000, and the common point for the second constraint is the 1500 and 1500. D'accord? So now after plotting the various equations on graph, we found these the border point A, B, C, D. A is given as 1000. A represents x1. A equal 1000, 2000 when x2 equals 0. So 2000, 0. And check D. D, it is 0, 600. The last constraint, the third constraint. Problem concern with 2 points C and B. Sorry, B and C. B and C are the point of intersection of lines or equation x1 plus 2x2 equal 2000 and x1 plus x2 equal 1500. So we need to solve this in this simultaneously. The intersection point between C and B, we need to solve this equation simultaneously in order to find the values of x1 and x2. Let's check the following table to show how we calculated. So now check the three corner points. A, x equal 1500, x2 equal 0. The intersection points B, x1 equal 1000, x2 equal 500. The next intersection point C, where x1 equal 800 and x2 equal 600. The last intersection point is x equal 0, x2 equal 600. Now we are going to substitute these values into z or graphical or objective function. Objective function state z equal 3x1 plus 5x2. When the corner point is A, where x1 equal 1500 and x2 equal 0, then z equals 3 times 1500 plus 5 times 0. So the result is 5500. Let's move to the next corner point B, where x1 equal 1000 and x2 equal 500. Okay, so z equal in this case 3 times 1000 plus 5 times 500, and we got 5500. Let's move to the next corner point where C, where x1 equal 800 and x2 equal 600. Let's substitute this value and we will get z equal 3 times 800 plus 5 times 600. The result is 5400. The last corner point where D, where x1 equal 0 and x2 equals 600. So it will be z equal 5 times 600 equal 3000. So once we are looking for profit maximization, then the best choice is to produce 1000 units of x1 and 500 units of x2, because this combination gives 5500 profit. Therefore, the maximum value of z occurs at B 1500. Hence, the optimal solution is to produce x1 equal 1000 units and x2 equal 500 units. Phases of operations research. There are 6 important steps in the process of applying OR. لدينا 6 خطوات مهمة عندما نقوم بتطبيق أساليب بحوث العمليات المختلفة. We know that each company faces some problems. In order to solve this problem, or in order to take an optimal decision to solve this problem, the first step is to define the problem. As an artist, say that firstly we have to recognize that the firm faces problem. The second step after the recognition of the problem is to define the problem. بعض الشركات تعمل على إخفاء المشاكل اللي بتواجهها، وهذا يعيق إمكانية اتخاذ القرار الأمثل، ولذلك يجب الاعتراف بأن الشركة أو المؤسسة تواجه مشكلة. The next is to define the problem. نعرف المشكلة. Its nature and its nature طبيعة المشكلة. Its nature. Its characteristics خصائص هذه المشكلة. Features. يجب أن نعرف المشكلة، نعرف طبيعة هذه المشكلة وخصائص هذه المشكلة. So, the second step is to analyze and define the problem. هي تعريف المشكلة أولا ثم تحليلها ومعرفة خصائص هذه المشكلة. The third step that to list various criteria to choose a sufficient alternative. عادة الشركات تضع عدة بدائل لاستخدامها لحل المشكلة المعينة. Various companies design various alternatives to solve the problem. Before that, we have to define or to list the criteria of efficient alternative. نضع المعايير التي على أساسها نحدد الخيار الأمثل لحل هذه المشكلة. Or to develop a model, then to develop a model نقوم بتطوير نموذج لحل هذه المشكلة من خلال اختيار البيانات كويس، وعلى هذا الأساس نقوم باختيار. Accordingly, we are going to choose the alternatives that suitable to solve the problem of that company. Then we are going to provide a solution and test it. الخطوة اللي بعدها to implement the solution، نقوم بتنفيذ هذا الحل أو بتطبيق هذا الحل. ثم to monitor and evaluate the output of that solution. بعد ذلك نقوم بشنو؟ بمراقبة وتقييم النتائج المترتبة على تطبيق أو تنفيذ الحل أو البديل. إذن لدينا عدة خطوات يجب وضعها في الاعتبار عند تطبيق أساليب البرمجة الخطية. هنا نتحدث عن المشاكل. أولا الاعتراف بوجود مشكلة. ثانيا تعريف هذه المشكلة وتعريف خصائصها ومميزاتها وطبيعتها. تحديد المعايير التي على أساسها نقوم باختيار البديل الذي يناسب حل هذه المشكلة. نقوم باختيار البديل الأمثل الذي يتناسب مع الحال هذه المشكلة، وبعد ذلك نطور نموذج على أساس تلك المعايير والبديل المتخذ لحل هذه المشكلة، ونميت هذه النموذج بالبيانات. ثم نقوم بتطبيق هذا الحل ونراقب هذا الحل ونقوم بتقييمه. ما ذكر قد يختلف من مرجع إلى مرجع آخر، لكن هذه الخطوات الست أيضا تعتبر خطوات في لتطبيق نماذج البرمجة الخطية. Example: given max z equal 3x1 plus x2 plus x3. So the required is to convert this primal linear programming into the dual linear programming. Now, as you see, the objective function is maximization function. And the coefficient of x1 is 3, coefficient of x2 is 1, and the coefficient of x3 is 1. Subject to this LPP has 3 constraints: for x1 negative x2 less or equal 8, 8x1 plus x2 plus 3x3 more or equal 12, 5x1 negative 6x3 less or equal 13. So there are 3 objective or 3 decision variables: x1, x2 and x3, and there are 3 constraints respectively. There are 3 constants as given. 3 constants are 8, 12 and 13. We emphasized before that the constraints of maximization must be less or equal. In this case, the constraint number 2 is more or equal. So we need to convert the second constraint into less or equal. How to do that? To do so, we need to multiply each term of the constraint number 2 by -1. So, solution. Let y1, y2 and y3 be the dual variables. Then the corresponding dual is min y equal 8y1 plus 12 8y2 plus 13 8y3. So 8, 12 and 13 are what? 8, 12, 13 are the constant of the constraints of the primal. As we mentioned before, the constant which at the right hand side of the constraints are 8, 12 and 13. So as let's return back, we need to fix if the second constraint is more or equal, we need to fix it as less or equal to be suitable for the maximization problem. But if we change this constraint to less or equal, it will be easy to convert the primal table into a dualistic option. Let us assume this. We are going to change technically the second constraint to less or equal. Then we will practice very different cases of the constraints. Now, the objective function now is min zy or min y equal 8y1. 8 is the constant of the first constraint plus 12 plus 12y2. 12 is the constant of the second constraint, and 13 is the constant of the last constraint. It's okay. Now let's move to construct the constraints of the dual. The constraints of the dual are constructed in the following manner. The vertical column, the first vertical column of the primal constraint will be the first row of the constraint in the dual. Let's see. The first column contains of the primal contains 4x1, 8x2, and 5x3 and 5x1. Then the first row of the first constraint of the primal will be 4x1 plus 8x2 plus 5x3 more or equal what? More or equal 3. More or equal 3. 3 is the coefficient of the primal table. And the second constraint will be negative x negative y2 plus negative y2 plus y2 more or equal 1. This constraint, the second constraint, contains two variables because there is no x2 in the third constraint. Okay, and the last constraint will be three y 1 3y1, check it, 3y1 plus 3y3 plus 3y3 more or equal 1. More or equal 1. So here we need to just check how to use the previous steps in the process of application.